All right. How are you guys doing? All right. I noticed today that I accidentally put your little participation assignment due in March instead of February for feedback for each other. So 5 of you happened to see it or whatever and filled it in as of like an hour ago. I updated that deadline for tonight. So if you don't mind, just a quick couple sentences. I think I also accidentally put it to like a file submission. I meant to just put like write in some text. So sorry, just stick it in a Word document or something. So I'm gonna wait on like sharing kind of a summary of all that with you till next time. And I realized I had a few slides specifically dedicated to kind of presentation, why we might care about communication in kind of the context of developing countries and stuff. So next time we'll talk at least for a little while about that type of thing, and give you that feedback. So please do that by tonight, or that's the deadline. So please do that by tonight. Okay, I've also now posted some instructions for you for the group presentations. So we've already done the first task, which was kind of that thesis statement. And then the other thing is going to be this cohesive group presentation, right? So you'll pair up according to what we filled out with the Google Docs. However, I will say that I've introduced a new complication here, that you have another choice, right? That choice to tackle this water treatment challenge. And if a few of you decide to do that, I'd have you present that instead of this group that was organized based on your research topics. I'm not going to ask anybody to change your research topics altogether, but if you really, really wanted to do a deep dive instead on this water challenge with, hey, can we use granular filtration, and make it into sort of a design paper, I'm open to that. That would be you backtracking on stuff you've already worked on. So I'm definitely not asking anybody to do that. But if that inspires you and you want to do that, I will certainly support you in doing so. Okay, but at minimum, I'd like some of you to present on this and to make some sort of maybe a brief report or a summary of what you just think might work. So if any of you would like to move here, please do so. This is for the presentations, right? Tell me directly if you're going to change your actual research paper topic, but assuming that nobody does, feel free to hop down here. We can get up to 3 or 4 of you to do so. If it turns out that we then only have like one person in a given other category, I'll take a look and see if maybe we can adjust something to make it more natural layout for. It's not one person just giving like a 20-minute lecture to everybody else, right? Don't want to put that on any one of you. Okay, so take a look. Feel free to do that. Change as you like. That link's still on Moodle. It's also in this Word doc that I put on Moodle. I don't know why it's doing that, but okay. For the actual presentation towards the end of the semester, essentially I want you to be teaching each other, right? Teach the class about something. Use this as practice to present. Excuse me. Use it as presentation, like developing that skill set, right? That's part of the class here, good communication skills. And so what I expect from each of you is to contribute to a group presentation. There'll be probably 3 to 6 slides per person, something like that. So you're each speaking for at least 5 minutes. It's kind of my expectation. Having your entire group come together and establish something that is, cohesive is part of that task. Overall, I hope that they can be about 20 minutes of a talk. can be a little more or less given, if we do have a group of, let's say, 2, maybe 10 to 15 minutes is the more likely target, but it would be fine for 20 minutes. I taught this class in the past when we had 30 plus students, and so I was like, okay, no more than this amount. Had multiple days to try to get through stuff. So we'll be a little more flexible here. We'll probably take 2 days to do the presentations and give feedback. I think I also posted, and if I didn't, I will, some expectations here on how I will grade and how you will grade one another. So I'll have each of you fill out a double-sided paper like this. You'll put your name on it, and then, for your own group, if you happen to be in this first group, you just strike that out and say, okay, that's not me. That's my group, so I'm not going to give feedback. But then you give feedback for the other groups. Okay, well, how informative was it on a 1 to 10 scale? How effective and engaging was the presentation? Give me your impression of that. I'll also be noting my own impressions of that. So your overall grade will incorporate both my impression and your peers' impression to an extent. And then, and this is something to address the, perpetual issue if somebody really doesn't contribute to a project, that's no fun. So you can give me your impression of how well you contributed to your project, and how easy was it for others to work with you, and likewise do so for each of your peers. And of course, this would be done a little bit more privately, so you can tell me like if there was a particular problem, or if you were happy with your group members and their contributions. So this gives me a lot of leeway to not treat one presentation graded. I can assign grades slightly differently for each person in the group if I feel that's necessary, and if your group ends up feeling like it's necessary, right? So that gives me a little bit of leeway to do that as well. So this would just be another 1 to 10 scale of effort and ease of working with. Okay, so I will take all that material in and grade accordingly. All right, so that's the plan for how you'll be evaluated. It's not meant to be, a particularly, it's kind of like the thesis statements. I saw a lot of you that did respond were saying, I really liked it was conversational, right? It's not meant to be your senior design where this is like, you must perform at the very max level, otherwise you just don't win it, right? This is, let's get engaged about a project, about a topic, and share that. So even amongst the few pieces of feedback I've had so far, almost all of you mentioned something to the effect of, hey, I really liked that people were excited about this. That was contagious, or that was gripping. I liked that. So that's what we want. Okay, any questions about that? I'll get some specific dates up later after senior design stuff. Okay. All right, so today we're going to talk about granular filtration. A little bit of an overview, but we'll get into some more specific compartmentalization. Talk a little bit about membranes today as well. Probably it's kind of related. Filtration in general, right? So we'll do more specific on that later. So we'll start with a bit of a comparison. So membranes versus granular filtration. There's actually 2 quite different approaches. We call them both filtration, but the general public might also call UV dosing a form of filtration, even though it's clearly not. So depending on kind of vernacular, how people look at it, it certainly makes sense to consider that granular filtration could act a little bit like membrane filtration, but in fact, there's a lot of important differences here. So if we have some sort of bed of media, and we'll have this filled with kind of sand grain type stuff, maybe some activated carbon, granular activated carbon, something like that. And we compare that to what happens when water is allowed to sift through that, comparing that to when you push water through a porous membrane. Now, if we consider a particle in membranes, that particle gets stuck because it's too big for the pores, or it's rejected. So sometimes we'll do cross flow, and so it just carries along its merry way. So membrane filtration is size exclusion. Granular filtration, turns out this is actually providing a lot of tiny opportunities for things like sedimentation. Sedimentation is when you let that particle settle. When it meets the ground, it kind of gets stuck. So in a granular media, this is kind of the same thing that happens in groundwater for the large part, is it's just the particles are meandering around and they touch something and get stuck. And then they stop, right, typically. So most of it is some form of adsorption, maybe impaction, and kind of the daily, your daily use example would be like a Brita filter. So a Brita filter is, if there are particles, it's going to catch them in the granules. Now, to be fair, the Brita filters are more aimed at dissolved stuff that would adsorb to the high surface area of the carbon. We could get into that separately, but it's still like that's kind of the deal, right? It's passing it through granular media. When we talked about swimming pool filters, they're typically these sand filters. Okay, so that's going to be sort of the baseline is granular filters use a process that actually works quite well with coagulation. So if you cause the particles to be destabilized, then they have a lot of opportunity to meet sand particles. They tend to stick to the walls of the sand a lot better that way. So it actually goes really well as a follow-up to a coagulation, flocculation, sedimentation step. And you'll end up having some of that happening inside. Membrane filtration, I mean, it could also follow it, but we tends to be more special cases, dealing with the fouling control and things. There's a little bit more operational costs and infrastructure involved. So membranes are used, certainly, but more commonly we'll do something simpler, which is gravity-fed, what we would call rapid sand filtration. Okay, so it's not impossible that we get this mechanical screening effect, large particles, but that's not really our design, right? So that's going to happen a little bit with maybe, especially with flocculation. Some large particles might get stuck, but typically we're looking at giving these particles time and surface area in the pores to meet one another, to say sedimentation here, to meet the bottom of the sand grain or the channel. Flocculation could occur because the particles are kind of encountering each other along the way, and then they get too big to continue. Interception, the particles kind of moving around and just touches the edge of something and kind of gets stuck. And impaction, the fluid is flowing, the particles with it, the fluid changes direction, and the particle just doesn't shift quite enough, and it impacts and sticks on the surface. So all sorts of little microprocesses we could look at that would cause our particles to be removed. Now, these are going to be loosely adsorbed, and so at some point, our media filter is going to kind of fill with this stuff, and then we'd get breakthrough of these particles making their way out the other end. So we ought to think about it as a sort of like Velcro. Eventually, your Velcro is going to get too much stuff stuck in it, and it's not going to catch anything else. Or in this case, it might be the stuff that got stuck first is finally like kind of coming back off. And so at some point, we have to clean it off. And so that's when we would typically backwash and flush stuff out. Maybe we agitate it with some air, some things like that. We'll show an example. But the point is there will be a maintenance step of getting this stuff back off. So as we think in particular about could we implement this in a developing context, we do need to consider that there will at least be some sort of training required, how to clean this, how to do so with water that's already been cleaned. Can we fill a tank of clean water and then reverse that flow somehow. And that, it's not too complicated, but it can complicate things. It might also be a reason to, to consider, okay, do we have pumps that we could reverse for this, or can we use gravity? Maybe we have the filter normally is below our water tank that, let's say our water source, and then we fill a water tank somewhere. Can we reverse, put one up and one down to do the backwashing? Can we do something like that to accomplish our tasks here? In practice, these often look something like a cylinder or a bed. Here's just a few examples of a cylinder. We've been donated this set of 3 granular filters, this little pilot thing, by a company for us to kind of use it as demonstration. Currently, there's a consulting group that's borrowing it. So if you really are excited about this kind of stuff, I could probably get you in touch and let you go see it in action. Usually it just sits in my lab like that otherwise. But it's not there right now because it's being tested. A few different media types are being used to test to see what method was going to work for a particular water project. They might be quite large, large bins there. When you have them in a confined thing like that, you're usually pressurizing them. You can go a little faster. Otherwise, if it's just an open bed, we would typically have just gravity to pressurize it. So these can go a little higher pressure. You still don't want to go too high because you'll end up channeling, like kind of breaking a channel in the sand, and water will just start cutting straight through in a sense. So there are some practical physical limits to how much pressure you can apply. But in general, most of these will have some way of saying, okay, normally we're going to flow, perhaps in this direction. In these pressurized systems, you could go in reverse and it wouldn't be much of a big deal. And then, okay, at some point, we can switch the valves and then backwash to go backwards, right? So this is what it would look like in a bed configuration where we have tons and tons of media just added to these large concrete swimming pool-like beds, and then you'll have some way to load your water onto it fairly evenly and to collect the backwash water. So you see these troughs here. So the media would end up going, probably about the size of this person there. Media would be all in that bed, and then water would be typically added. In this case, there's probably 2 beds next to each other with a channel in the middle. And I think we've got a video I'll show you. And water would be added in, spill over the sides here like that for loading the water onto the filters. That would just happen continuously until we need to backwash, and then we'll do exactly the reverse and drain the dirty water out these troughs. So that's a pretty typical arrangement. You'll often have sort of larger grains at the bottom with some sort of a mesh protective layer type of situation to kind of keep your media there. And then the smaller media would add on top of this. That would keep it all in place, allow for water to be going through it, but the grains not letting them escape. Okay, so here's another example. So this is probably several beds combined next to each other, and just in typical operation might not look like a whole lot, during operation. Okay, so just a quick bit of background here and typical design. So I had already mentioned this, I think last time when we were talking about this treatment task that we have. It was actually in the 1800s we started the first kind of sand filtration designs that I'm aware of. And these are biosand filters or slow sand filters where you'd allow water to pile up on a bed of sand of some sort and give it plenty of time. So a residence time of days instead of minutes, or I think a rapid sand filter would, probably be minutes, right? So that would give whatever stuff is dissolved in the water a chance to be biodegraded. based on whatever biological materials on the sand itself. So biosand filter is kind of acting at a bit of a different level, but you are getting some similar particle removal. And in that case, you probably don't need any backwashing because the biological activity is munching on all the particle matter. And it's just going to be a slow seeping process. And so you know your flux is not going to be very high. Okay, typically in our rapid sand filter, in more, these days conventional design, would be some mixture of sand, maybe anthracite, which is kind of activated carbon stuff, or like a mineral that's kind of like that. Some combination of those materials. And if we're using activated carbon in particular, that does a good job having high surface area for stuff to stick onto it. And sand grains, all of these materials are generally pretty cheap, and we want them to be a pretty reliable size. So that's another kind of design aspect, is we want to have pretty good uniformity there. Okay, so then when we're operating, we're going to let these operate for a little bit of time, let all the sand settle into place. Any particulate matter that was kind of disrupted recently, let that discharge. So again, if you've ever used a Brita filter or something like it, one of those brands, you pour a bunch of water in and it's like going through this little thing. Some black specks fall out and you're like, ew, gross. Like, what's up with this? Well, that's filter ripening. And it probably gives you instructions to say, oh, flush a gallon of water through first before you use it, or something like that. That's exactly the same deal here. Is there's some small particles and the grains haven't compacted quite yet, and you got to flush it a little bit. So that's the filter ripening. That usually just takes, maybe 15, 20 minutes of operation, sort of warming up the filter in a sense. And if you think about it, if you just backwashed and kicked up all the junk and particles around, it's all shaken up, and then you reverse flow once it's clean enough, well, there's probably still some dirty stuff in there that's loose and that could just come right out as soon as you start pouring water the other way. So we just don't want to assume it's all the way clean yet. And in fact, if you look at the turbidity, that's exactly what you'll see, is the first few minutes of operation, it's kind of dirty, and then it starts coming out pretty clean. Okay, another step would be backwashing. That's pretty obvious. We're just going in reverse. Sometimes we add a bit of air bubbles first, shake everything up quite a bit, break everything loose. That's typically enough to regenerate one of these. If we're just, the process itself is just that particle capture, and so we don't have to do like fancy chemical cleaning or anything like that, because we're going to clean up our water more later, right? So it's okay if some viruses are getting through, and I mean, we expect viruses to get through, but it's okay if bacteria even are in there, because we're designing to take care of that later. Okay, then a couple terms then, head loss and turbidity. You know about turbidity. It's really a measure of particles in the water based on how much light is scattering. Head loss we'll use as a term to describe the pressure difference. So as the filter gets dirtier, we have to use more pressure. So head loss specifically means that pressure drop across the filter. So if we had 1 meter of water stacked on top of the filter, that's pushing, we'd call that 1 meter of hydraulic head for water. It's kind of the common term used there. That means we have a certain amount of pressure applying. Now, if we get the filter dirtier, we have a larger head loss, meaning that it takes more pressure to get the same amount of water through. So if we're filtering a constant amount of water because we need to meet a constant demand of water, then what will happen is that water will just accumulate higher and higher on the filter in order to continue to treat that amount of water. It's actually very convenient because we don't have to like turn the knobs and figure out, now we have to pressurize it a little more. Gravity just does all that for us. It's great. But at some point, if it gets too high, well, we have risk of that fissuring and the short circuiting of the water. So at some point, we got to stop our operation because the head loss was too bad, right? So those are kind of the key terms. for operating a granular filter. Turbidity, like I said, I think you're all quite familiar. Now, one thing to note is this really doesn't classify the size of the particles very much. It's just particles that scatter light. And any particle that's around the size, I think about up to or down to about half the size of the wavelength of light can scatter. I'm not exactly sure on that, but I think that's about right. So 400 nanometers of light, that's kind of the violet, that's on the verge of ultraviolet. So anything, that's kind of the lower range of our vision. So something like 200 nanometer particles will probably scatter light, maybe a little smaller than that, probably not much smaller than that. So we'll just say that could scatter. And that would also be the same as saying 0.2 micrometers, right? So if we have particles that size that should be scattering, should expect they could scatter light. And if you look in the lab and you've ever dealt with any sort of sample handling, you might have used a syringe filter or something. A lot of times they'll have a 0.22 or 0.45 micrometer filter. And that'll actually usually do a pretty good job removing anything that would scatter light. So that's the kind of stuff we're thinking about. Anything larger than that happens to stay suspended. And we might look at the word problems we've looked at before. We might expect having anything from 0.2 micrometers up to 10, 20 micrometers. Silt particles that were 0.01 millimeters, that was 10 micrometers, right? So anything from 0.2 to, 50 micrometers might be something that we'd be thinking of here as particles that we're trying to deal with. We saw sedimentation can deal with stuff that's, especially if we add coagulation and stuff, then maybe down to 0.01 particles can be removed. And if we do the coagulation, maybe we're capturing some of the smaller stuff. But there's definitely some that could still be difficult to deal with. And the turbidity, by the way, so all that to say, turbidity is just the amount of light being scattered. That's not telling us any information on what kind of particles they are. It's kind of giving us some information on how many there are, except that the size versus scattering, a few large particles can scatter about as much light as a lot of small particles. So there is some discrepancy there of if we care about the number of particles, which we may or may not, it's not an exact metric for us. It might be an important metric if we're trying to use ultraviolet light, for example. How far is that light going to make it through the solution would be an important question. Okay, we typically measure it. I think we talked a little bit about this. There's a thing called a Secchi disk. And at some point, if you drop a device like this into the water and measure the distance, at some point, you're no longer really able to see the difference between the white and the black panels here. And, the thing just kind of disappears or becomes one little blob. At that, that's one way of measuring, okay, at that point, the light that's scattering there is not making it into there and bouncing back and reaching me back. So we can correspond to that to some level of turbidity. So there's a few different ways of doing that. We had the little device from that Del Agua kit you could maybe use in a similar manner. At what point can you no longer see or distinguish something if you're looking through a tube of water? So it's kind of there's a few ways to do it. You can use a UV-vis spectrophotometer, just check it at a particular wavelength and use some calculations, get an estimate that way. Okay, so in terms of monitoring turbidity, let's say we have some sort of monitoring happening, then if we're taking a look then at what's the time that we need to stop operation? Well, we can either do the head loss limit. So, we have too much pressure now, we're going to go ahead and stop. Or we could do a time limit. We know we have to backwash every 48 hours, so that's what we do. But either way, we generally will also use some sort of turbidity limit in like typical operation. So in the case of a scenario like, let's say, in a developing country, probably time limit would be the better way to go, depending on how you design something. But it would be kind of important to train people to pay attention to the turbidity, but it might not make sense to give them all the formal technical stuff, because that might burden them to be unsure of themselves. Whereas they might be pretty sure of themselves to say, oh yeah, that looks dirty, that doesn't. Right? That might be enough training to monitor, to make sure things are not failing, and also, give some instruction to say, okay, you really should backwash every 36 hours, 48 hours, whatever. Maybe it's weekly if it's not a huge amount of water going through, and something like that hopefully would be a nice practical solution, because they could see very clearly, oh yeah, that backwash is pretty dirty, right? We're removing some junk, so that's good, and we don't want that, right? So it might be a good opportunity there as a convenient way to do the education there. Okay, so turbidity, if we were to look at a plot over time, if, let's say, our cycle time starts here, we do some rinsing for the first few minutes. So, I don't know, like a quarter of an hour. And then sometime way out here, we stop and do the backwash. We'll call this 48 hours or something. So not quite drawn to scale here, but I wanted to say what we typically see is if we have some turbidity, and maybe we say there's a cutoff, we don't want anything above this level. What we'd probably see during the rinse phase is we're above that cutoff, but it quickly goes down. And then we start our filtration, and then we slowly have our turbidity rising from that, right? So the time we cut off would, typically, in this case, we probably ought to cut it off there if we set some limit to say this amount of turbidity is bad. That's our limit. We would cut it off before the 48 hours in the way I drew it this time. Or maybe that's just heuristic and it's somewhere around here is a good time to stop, and we notice, yeah, it always kind of reaches at around 48 hours, and that's good enough. Whatever the design, however we design it, that's the type of design or type of thing that will happen. Okay, so just another look at it would be to plot the head loss. This is a lot simpler. This is just simply going to raise over time. As soon as we start filtering, even ripening, it's not really going to do much else than a line, right? It'll take more and more pressure the dirtier it gets. Nothing too fancy there. And just as when we talk about a filtration cycle, just to be clear, we will have really 3 phases, maybe a 4th if you count the air purging separate. We could say we'll be rinsing or ripening here. Then we're producing water, so we have production. Then we will stop and maybe do air purge and backwashing. Air is kind of optional and might not be that practical for, let's say, a small decentralized system. Could imagine that having an extra pump for air just for that probably wouldn't make too much sense, right? In the scale of a municipal treatment plant, and maybe they already have blowers for other purposes, diverting some there would make a lot of sense, or if it really improves their backwashing. So typically this might be a few minutes. The production hopefully goes, for a long time. So this might be anywhere between 24 to 96 hours in a municipal situation. Perhaps we can do something weekly for a small scale operation, or maybe even longer than that. How many of you that have done swimming pool maintenance, do you have to backwash the systems? How often? So the filter's probably not working. Mhm. Okay. And do you know, were they continuous operation? Probably. Okay. Not yours. So it just wasn't operating? Did you just turn it on for like a overnight or something, or like what was the?
You don't run the pump all day, so it's not filtering water all day.
Okay. Because some of them probably do. Like if you have, like I don't know, was this like a what was the context? Either of you like have, so like a neighborhood pool or what?
Like one of the house.
Okay, so a household scale. Was yours like?
It was a public pool.
Okay, yeah, exactly. I was gonna say it probably depends, like if it's a water park, for example, or a public pool compared to a private, you know, somebody's house sort of thing. One probably needs it continuous, or you'd like for it to be, and the other you really don't need it all the time, right? And so then you're probably gonna address the backwashing even as needed in that sense. So there you have it. And so not sure about when, but weekly probably for that one. That makes a lot of sense. And there probably, I would guess, there's also going to be a difference in size. Like there's probably several large cartridges for that one, right?
Yeah, we had two sand filters.
Okay.
Like,
Okay. And then yours are probably a little smaller, I would bet.
It's still pretty big. It's about this big around.
Yeah. It's funny. My family has a pool. And I know they're back there. I just haven't actually gone and played with them yet. So they moved there, sometime after I had been out of the house. So I was like, I haven't been directly involved, but I was like, well, I should be able to do all that. I could teach you about it, but can I do it? I need the manual. Okay. So yeah, and so that would be the typical cycle. And the swimming pool systems are a pretty good concept or scale if we were thinking about treating water for kind of a decentralized or small community system. And if you think about it, I think the Olympic swimming pools are like 1 million gallons or something on that scale. And maybe you want to treat them like having a full water exchange every so often. So, as regular swimming pools much smaller than that, you could think about, okay, well, what's the flow rate through our filter to achieve the kind of treatment we need, right? And just thinking about it in that way, maybe if you had an Olympic swimming pool or a facility with several, and you were trying to get water changed twice a day, you're starting to talk about larger, pretty big filters then, and flow rate capacity. Okay, so that's kind of the scheme, the general gist of granular filtration. And from the reason we, on the municipal side, and maybe still a little bit relevant for community scale type things, what we have to realize is we can only produce for so long. And then we're going to use produced clean water to wash the system. So we are wasting water when we rinse, sending to waste the water that we rinse with and the water that we backwash with. So we have to have something to deal with all of that. In the case of treating drinking water, this is obviously dirty stuff, but at least it's not, direct like fecal matter, right? So we don't want to be exposed to it, but it's probably okay to apply that somewhere, as fertilizer or something would not be as potentially hazardous as like a wastewater treatment sludge. But effectively, it's going to be almost sludge-like. There'll be lots of particles in it and lots of junk. So there's a few things to think about. How do we deal with that? How should we dispose of that? And also noting that if we can produce 100 liters a day, well, on average, are we using 10 of those to clean it? Well, then we're really getting 90 liters per day. So just some of that, and we could do some simple math with this, and we tend to do that in my other class. Okay, so wanted to show you an example of backwashing here. Okay. So this is an air purge happening. This is one of those filter beds, and it's as that air is being pushed, there's still some water standing on it, and they're just scouring it with a bunch of air, just pressurizing a bunch of air underneath. You can see how nasty it looks there. So this would be pretty typical, and we see those troughs that we'll see them in action in a minute. There's another filtration bed on the other side here as well. So this is a pair of filter beds. Going to do that for a few minutes. I'm going to mute that for a minute. So at this point, now we are muting like they are. It's well, if I turn it on, it's extremely loud screech, and yeah, no fun. Because they're now priming the pipes that they were just using, so they're trying to get all the air back out, getting it ready to push water up through. So the video did a good job capturing how uncomfortable that is. Okay, so then. All right, here we go. So now they're about ready to push water back through. And there's still going to be a lot of air trapped in the sand grain, so we'll see bubbles coming up still, but
Film the water for a bit. It's all wow. It's all bubbly. This is how they make root beer. Giant.
Classy. Well, you'll see in a moment that the resemblance is striking. It's all bubbly and stuff, right? Okay, so then they're filling up the beds. And there's your ruby. So that's all the particles that would have made it through, and unfortunately didn't, right? And so they've been concentrating those particles for somewhere between a day, a couple days, something like that, and now they're all collecting it. So you can see that's a fair amount of water that you need to use to clean it back out. And this will probably operate for 10-15 minutes. You typically will push water backwards through it at about a similar rate, maybe up to twice the speed as you apply it to the filters. And in this case, they're taking it all through that channel, and that's going to go to wastewater treatment of some sort. When they finish this, they would flip it around and go the opposite way and be treating the water, and it would probably use that same exact channel and just be using the water probably had just been in the sedimentation. Okay. All right, so that's pretty neat. That's kind of the scheme of it on a large scale. I guess if you've done so at like the pool scale, I don't know, it might just drain straight to a sewer or just kind of discharge into the yard or whatever, depending on your situation. You'd probably see something kind of similar. Okay, so I want to also talk a little bit about an alternate granular filter of sorts. And this is a little bit more applied in terms of how can we use a similar process in developing contexts, and that would be a ceramic pot filter. And this is honestly something kind of between the granular scale and a membrane scale. So if you take ceramics, and if you've ever played with clay and done a ceramics class or anything like that, you'll notice that sometimes they're kind of porous once they're fired. Lots of little bubbles or holes. And they can still be solid, but porous. And then you'll typically coat it with a glaze and fire it again, and then that kind of seals it. And in fact, if you just look at this wall, you'll see like it's painted, but the concrete blocks underneath look like they might be a little bit porous, right? It's the same sort of idea, right? There's some structure there that, if you didn't coat it, or if you made it just right, maybe you could get some water to go through it. So there's potential then to use ceramic pots as a way to sift water. And I say sift because it's not quite filtration. I mean, it's kind of filtration. The action is going to be a little bit of this size exclusion for large particles. It's not, typically if you're going to get a reasonable amount of water through, it's not really small enough to exclude bacteria, especially not viruses. So you're not necessarily size excluding them, but there's a couple things that can help a little bit. So if the pores are, let's say, 10 to 20 microns, bacteria can certainly get through, but maybe it's a thick enough layer where a lot of them get stuck. Okay, so maybe you'll slow them down so that they're not as likely to make it through. Some people have proposed adding some silver nanoparticles that can do a decent job of killing bacteria on their way through. Some things like that. So these ceramic pots, presumably, if you have clay, which you can often get clay in a lot of locations in the world, then make a pot and send it through a carefully controlled process. Then there's a good chance you can make clay pots that can do that filtration. So the idea then is to fill one of these, and you'll have like a dual bucket sort of system where you have a clay pot resting in a bucket, and then you fill it with water, and then that water drains through into the bucket, and then you have a little spigot, and you have cleaner water than what you put into your clay pot. So it's kind of a neat idea. It's pretty simple to operate. You still have to concern yourself with cleaning it out and preventing contamination, especially preventing contamination of this bucket itself here. You can see even this guy holding it is touching the outside of that pot, and that's a potential source for contamination, right? Because you want to keep anything on the outside of that barrier clean. So there would be some important instruction to go on and stuff. These would typically be pretty robust. It's kind of would be a lot like, a little terracotta potting plant, plant holder type thing. Would be a pretty good feel of, you could break it, but it's not going to break if you bump it. So you'll remove a fair bit of turbidity. You'll get some bacteria. You might also get the same removal of some of the parasites, and that, the schistosomiasis kind of stuff would probably be removed. It'd probably be too large. But again, the kind of the caveats are, well, you might end up getting biofilms forming as a potential concern. And eventually the flow rate's going to slow down. And also, if you think about it, pouring water into a pot like this and letting it dribble through for some time, how much water are you really getting per day, right? So that we talked a couple days ago about, well, what should we design for this home treatment system? Well, we thought 30 liters per person a day would be great, but at minimum it was like 3 to 4 for cooking and drinking, right? Or 4 to 7, something like that. So if you're going to use this for cooking even, in addition to drinking, I'm already feeling like you're probably going to need several pots, several of these for one household. And so there's some practical considerations, like how many do you need? Is that sufficient? How much of a pain is it to use and maintain? And then you probably ought to clean them with the water that you filtered with. So practically speaking, I have some questions about what the cost effectiveness of investing into this versus investing into even let's say disposable things like the Procter and Gamble's packets, right? Well, if it costs, let's say $20 to get one of these and that'll work for a couple of years, but then there's a lot of maintenance. How does that compare to $20 worth of coagulant stuff, and along all those things? I'm not here to make a case one way or the other. Just that question arises in my mind. Okay, I mentioned one of the things people have done is added colloidal silver or silver nanoparticles, and it's a pretty neat idea because the silver particles have this cationic charge that tends to exert an antimicrobial property, and actually some of the water fountains, like I don't know if the ones here, but I've seen some where they kind of have this like grayish plastic coating on the handles. Some of those are coated with silver nanoparticle stuff to try to help prevent contamination and transmission of disease and stuff. So we've used them around in different places. There's a little bit of concern. They're slightly toxic, but they probably shouldn't be coming out in large amounts. And this wouldn't be like an accumulation type toxicity, I don't believe. So it's probably fine, but there is a question there. Are we also introducing a toxin? Even still, they would continue to need regular cleaning. Biofilms will be able to form anyway, maybe some dirt particles, and then you get stuff happening. So it's not a foolproof like self-cleaning solution. And there's also a question, if you're doing the silver addition, is that sustainable in terms of like, do you have to reapply this stuff? And how much does it cost to add a precious metal to these? Now, you're presumably using a very small amount, so it may come out in the wash in terms of just forming like the cost of producing these in the first place. But some questions there, and some possible benefits there. So this is what it would kind of look like in practice, where you'd have your dual bucket system. Water would seep through, and over time you'd have that treatment. You do want to be careful with the lid versus, to have some kind of a lid to keep things contained, but also to pay close attention to that transition to avoid contamination, right? Okay, so a couple other options, and these are a little closer to the types of things that might be applicable, if not a sand filter for this specific home scale system. Maybe membranes. I think this one on the right is actually a ceramic pot as well, I believe. It just looks kind of fancy with a dual chamber here with a pot. If I'm not mistaken, is something like this, and then you have water storage down here. Might be something slightly fancier, but I think that's a ceramic pot, nicely housed. But there's a life straw or lifesaver things. You may have seen at some point people were kind of excited about a literal straw that had an ultrafiltration membrane in it, and with the suction you could provide with your lungs, you could actually pull water through it and drink. Doesn't seem like it would be the most comfortable thing, because if you've ever like tried to drink a milkshake and you just didn't want to come because it was too solid or something, it's like you're exerting a lot of force, and then it just, that wouldn't want to always have to drink water that way. I mean, for a milkshake, sometimes it's worth it, but so there's that lifesaver straw is kind of a neat thing, but maybe more practically, having like this setup right here, you can see a couple straps and this bag that you could fill with water. Pull that bag and hang it somewhere, then you have gravity to work with, right? That's something that we can lift a couple gallons of water and then use that gravity, right? So that's this particular filter. I think it might even have a setting where you can backwash. I'm not sure if that one needs or has that, but so certainly membranes become an interesting option for kind of point of use systems. In fact, the second time I was in Nicaragua, we brought I think a GE Sky Hydrant. This thing here is a membrane filter, and we're just kind of checking it out. It was a little crazy to bring that entire thing and fly with it and everything, but we did it. And so these are a pretty interesting option. Again, if you have a bit of gravity or pressurization, we can put in this Sky Hydrant, and these are designed typically for about 10 meters of elevation of your water, and that's enough pressure to do this ultrafiltration, and that actually does a pretty good job cleaning. And these ones do have a backwash capability. So membranes, I think I've got a section on that specifically. If not, I'll plan to develop one. But membranes, we generally backwash them a little more often than granular filters. It's more so to prevent the surface of the membrane from getting too gunked up, fouled, because that ultimately makes you use more pressure and stuff. So it's a bit of a different process rather than, like, usually membranes will have some water, clean water going through, and some dirty water that just goes away. If we're doing like if we're doing operation in a cross flow thing, that kind of helps keep the membrane a little more clean. So there's a few things to consider there and how to design it, but there's a couple neat membrane systems like that could also be used. Okay, so that's kind of what I wanted to say for granular filtration. Any questions or concerns for the presentations? I think for those of you going on the trip, we've got meeting time planned next week. All right, how many of you, show of hands, want to present on this? Anybody? Okay, maybe. All right, good. So feel free to put a maybe there. Take some time to give it some thought. That's totally fine. If I would say if you find yourself excited about it, go for it. That's that'll be good. And if nobody ever does anything with it, I might have to assign some people, like, okay, participation assignment, sketch an idea, right? I might adapt a little bit, but we'll see. Okay, so I think that's probably it for today. So next time we'll talk a little more about communication and probably get into I think sanitation from there. Maybe I'll do some membranes.